Hello everyone. Let's look into the placement and routing stage of the physical design flow. So the first step and the very important step in this particular thing is to bind the netlist with the physical cells. Okay. So what does this exactly mean? So this means that let's say we have this particular netlist with all these gates, and the shape of these gates represent the functionality of these gates. Okay, so for example, if this is an OR gate, the shape of this OR gate determines that this functions as an OR gate. But in reality, we don't have shape something like this. But what we have shapes something like a box. So for example, you have this flip-flop, okay, which is a square shape over here. It's actually a box of square shape or rectangle shape. For example, you have this NOT gate, which is of some triangle and a circle over here, but in reality it's a box. It has got some physical dimension. It has got a width and height. It has got some width and height of this particular cell. Similarly, for this particular AND gate, if you see, this is the shape, but it has got a physical view of something like this. So in reality, it is not something like this, but it is a box in internal, where this particular box will function as an AND gate. Okay, and similarly for flip-flop 2, the flip-flop 2 is also a square box. Okay, so what we have done is we have taken the real time, we have taken the views of this particular thing, of this particular gates, and given them a physical dimension, because that's what is actually present in the real world. In the real world, we don't have this kind of shapes, but we have square shapes and rectangle shapes. So we have taken these gates and given them a proper shape, a shape and size. So basically we have given them a width and a height. Okay, similarly what we'll do is we'll take each and every component of this particular netlist and give them particular shape. Okay, so this is this particular section of the netlist. This is the third section of the netlist, and this is the final fourth section of the netlist. So each and every component of the netlist has been now given a proper width and height, a proper shape, and these blocks are already have they do already have a proper shape. So let's not worry about that. And now what we'll do is we'll take these blocks and remove these wires. Let's talk a bit about this particular thing. So these things are present in a shelf, and let's call that shelf as a library. So a library is basically a place where you will find all kind of books. These are like books, and these are like different books that we have available in the library. Not only this, the library also has the timing information of this particular gate. For example, what is the delay of this particular gate, what is the delay of this particular gate. So all this information are present in a huge set, and it's called as a library. Though the library can be classified into two sub libraries. One library might consist of only of the shapes and size, and one library might consist only of the delay information, but let's call it as a library for now. Okay, so the library will have the following information. It will have the width, height of each and every cell. It will have the delay information of each and every cell, and plus it will have the required conditions of this particular cell. Okay, so for example, at what condition does the flip-flop emits the output, sends the input to the output, at what condition. So there is something called as when condition. So all this information are present in the library. Okay, so along with this information, it also has various shapes of this particular various shapes of this particular gates. So for example, in this particular scenario, if you see, this gate has got a fixed width and height. the library also provides you some options for this one. For example, there will be another option in the library of the same cell. This particular cell, let's say 2, functions as some give some functionality. Let's say it is an AND gate. This 2 will also function as an AND gate, but it will be slightly bigger in size. Okay, and the second difference between this particular AND gate and this AND gate and is that since it is bigger in size, it will have least resistance path, so it will be faster compared to this one. Similarly, you have other options as well. You have even bigger cells than this one, so this is even faster than this one. It is bigger in size and faster than this one. So basically a library has got various flavors of each and every cell. So let's say for this particular cell, you have 3 different flavors of the same cell. You have two of a bigger size, lesser delay. You have 2 of a even bigger size and even lesser delay. So you have various flavors of cells in your library. We can pick up what we want to, based on the timing conditions and based on the available space on your floor plan. Okay, so this was about library, and we will be talking more about library, more about the size, shapes, and more about the timing information that the library consists in a separate section. Let's not get into those things over here. That's a separate video on timing. So we'll be talking about the library constructs and everything in a separate set of videos. But in general, in a broader sense, library consists of everything. It consists of cells, shapes and size of the cells, various flavors of the same cells, and the timing information, the delay information. Okay, so let's keep it to that level till now, and let's move ahead. So once we have done that, once we have given proper shapes and sizes to each and every gates, the next step is to take those particular shapes and sizes and place it onto the floor plan. So let's see what we have till now. So we have the floor plan. We have a well-defined floor plan with the input and output ports defined properly and placed properly. We have this particular netlist. Okay, basically this is our design. This is our full design, and we have a shape and size given to each and every component of this particular netlist. So we have the physical view of the logic gates, and we have this particular floor plan. The next step is to place this netlist onto this particular floor plan. And how do we do it? Let's look into that. Okay, so now this netlist doesn't comes into picture, but this is what comes into picture. Though we have to follow the connectivity information from the netlist, but we have to take this one if in the case of physical design placement. Okay, so let's do that. So this is our floor plan, and this is the pre-placed cells that we already had from the previous slides. Okay, so let's keep it. So these steps are done in the floor plan stage. So the placement stage, the stage where we do the placement, that will make sure that this particular locations are not affected. They are not moved. They are kept as it is. And the second thing that it will take care of that there will be no cells that will be placed in this area. Okay, so these two things we have to take care. Let's move on with the placement step. So you have this particular netlist, and we have to take the physical view of this particular netlist and place it over here. For example, we'll take this. Let's say we'll take this first section. So if you see, this flip-flop 1 is close to input port D in 1. Flip-flop 2 is close to D out 1. Okay, so let's place it in that fashion. So you have flip-flop 1 which is placed close to D in 1. You have flip-flop 2 which is placed close to D out 1. Okay, and you have this combinational cells which is placed close to flip-flop 1 and flip-flop 2. So let's do that. Okay, so you have this particular combinational cell which is placed close to flip-flop 1. You have this combinational cell which is placed close to flip-flop 2. So if you see, logical connectivity is being maintained, and since this particular section of the circuit interacts with the D in 1 and D out 1, they are being placed close to wherever they are. Because if let's say D out 1 was over here, and if we had placed flip-flop 2 somewhere over here, then the time required for this flip-flop 2 to communicate with its own D out 1 would have been huge. So we have been taking care of that particular huge delay in the placement stage itself by placing the flip-flop 2 close to D out 1 as far as possible. Okay, similarly we'll be doing for the next stage also. So let's say we have this particular section, D out 1, D in 1, flip-flop 1, flip-flop 2, D out 2. So we have taken this particular section and placed it over here. We have put flip-flop 1 over here and placed it close to D into, not exactly close to, but there are some reasons why we placed it close to flip-flop 1. We'll come to that in some time from now. Okay, flip-flop 2 is being placed close to D out 2, and there is a peculiar case over here where we have abutted the cells, the combinational cells. So now if you see, the delay between flip-flop 1 and 1 will be very minimal. The delay between 1 and 2 will be minimal. Similarly, between 2 and FF2 it will be very minimal. Okay, so we have done this on due to some reasons, and we'll be coming to those reasons in some time from now. So what we'll do is, since we have already placed two sections of the logic and I'm already running out of time, we need some more amount of discussions for this section and this section and the other place where we are identifying the reasons why we have placed D into in such a huge distance, and how do we place the remaining ones. So let's try to cover all of them in the next video. Thank you.